Welcome to today's webinar. Our topic will be the design of rigid and pinned steel connections in RFEM and RSTAB. My name is Moritz Bertram and I will lead through the webinar today. My colleague Lukas Sühner, who is responsible for the joints modules, will answer your questions. You can ask questions using the control panel, which you can show and hide usually on the right side of your screen, and type in your questions in the corresponding box. Also, you can adjust your audio device in the control panel if necessary. Should your question not be answered during the webinar, we will send you a follow-up email with the answer. Now we will have a quick look at the agenda. We will have a brief look at the modules that we have for designing steel connections in RFEM and RSTAB. And we will do a design of rigid and pinned connections for a practical example using the two of the joints modules. What kind of modules do we have for the steel connections? We have, it's always two modules defining the same. One is for RFEM, one is for RSTAB. So one is RF joints and the other one is just joints. So we have the joint steel DSTV, which is some kind of design collection for standardized connections according to the ring binder of the German Steel Construction Association, DSTV. This is a collection where you can look up permissible internal forces for a standardized connection. This is just for Germany, so we'll leave that out today. Then we have the joint steel pinned. This is for designing pinned connections using web cleats, fin plates, short end plates and end plates with cleats. We can do connections between columns and beams using the web or the flange of the column, and connections between two beams. Loading can be shear or normal force or a combination of both. Then we have the module joint steel rigid, which can design a combination of a bending moment, normal force and shear, and we can do a rigid beam to column connection with a rigid end plate and beam to beam connections with a rigid end plate again, or a rigid splice plate. Then we have the module frame joint pro, which can do knee joints, T-joints, cross joints, joints with continuous columns using I-profiles. The advantage of this module is that it does a preliminary layout of the bolted connection due to the existent internal forces, which can be specified in the design later on. And for the modules in the frame, I will do a design later on, although I will concentrate on the joint steel rigid because this is the newest module of the joints family. There are a couple more modules for connection design. This is, for example, joint steel column base, which can do rehinged and restrained column bases. Normally this will be a connection with a base plate with or without stiffening, and for the restrained columns we also have a bucket footing as an exception to the rule. Then we have joint steel tower, which does a design for pinned bolted connections of members in lattice towers, and we can do a design of 2- and 3-dimensional joints and column splices in this module. Then we have the module joint steel Sigla, which does a design of brackets and end plates from Sigla, which is a producer of fastening systems. And last but not least, we have the module HSS for the design of connections with hollow cross sections, also doing 2- and 3-dimensional framework joints. Now we have covered the modules so far, and we can go into the example. So this is RSTAB. You can do all these things also with RFEM with the module RFJoins. We have here a simple steel framework with 3 levels. It's 12 meters high. We have a space for a vessel in here, so pretty normal thing. We will not do any modeling or loading today. Modeling has already been done. The loading also, you can see we have load cases and we have combined them automatically for getting load combinations and result combinations for the ultimate limit state and the serviceability limit state. The connection design will be based on the result combination number 1 for the ultimate limit state. Then we have the module RFJoins. I can get that over the navigator or over add-on modules, connections, joins. And this is like the main module of joins, which combines all the sub-modules of joins. So we have column-based, pin joins, rigid joins, tower, DSTV, and Sigla, as I mentioned before. Now we want to do a pin join. You can select your desired joint via the pictures in here. So for the column base, for pin joints, for rigid joints, tower, DSTV, and Sigla, or using the drop-down menu. We will do the pin join now, and it's supposed to be a beam-to-beam connection using a fin plate. That's it for the first window. We are using the DIN National NX now. And we go on to the next window, nodes and members. Here we can select the place where we want to do the design. So I select a node. In this case it's node number 91. It's one of these platform beams. They all have pretty much the same load, so it's going to be the same connection for all of them, more or less. And I do that just for this example. Okay, node number 91, I click OK, go back into the module and get the questions. Should the geometry of the connection be set to the default geometry? I confirm that with yes, and the program automatically recognizes the parameters and the construction status of the members. In this case, these two, 149 and 150, are the supporting beams, and 168 is the beam that we are doing the connection design for. And we go on to loads. As I already mentioned, we are using result combination number 1 and go on to the geometry. Here we can have a quick look at the picture. This doesn't look too good because the lower bolt collides with the flange of the beam, which we don't want. That wouldn't work. And so we have to do a few adjustments for the connection, for the geometry. We don't need to do anything for the arrangement and the notching, but we have to also the connecting component is okay. The dimensions of the fin plate should be changed. So I changed that to a height of 80 millimeters and a width of 150 millimeters. The thickness is okay. You also see that on the right side in the picture, this the measurements instantly change as I change them in the table. So you always are in full control of the things that the program is doing. Then we want to have a look at the bolts on the beam. Here the shear plane is not supposed to pass through the threading of the bolt, so I uncheck this box. We want to have a regular bolt distribution and horizontally symmetrical placement. That's okay. We changed the bolt diameter to M16 and the bolt strength grade to 10.9. And the only thing, then we changed the horizontal bolt rows to 1, which we can do after we've changed the vertical bolt rows to 2. So we have to do 1 first and do the other later. And then we changed the horizontal bolt to edge distance to 40 millimeters. Okay. Sorry. The next thing we are going to do is change the size of the weld, because 4 millimeters will be enough in this case. Okay, this looks good in the picture now, and we can do the calculation. This goes rather quickly, and we have a design ratio of 41%, where the bending of the fin plate is governing. This connection could, of course, be optimized, changing the geometry parameters. But this is not the purpose of the webinar. You can edit all the parameters for a better ratio, and we will leave that here. We will just have a quick look at the results. We have already been at the summary. The geometry is pretty much the same as for the input data, as you see. And then we can look at the design by the load case. We can look at the design by nodes, which is just for one. And you have always the chance to look at the design details for understanding what the program does. Then design details for every check, you can have a look at that. And then we have the graphic window where we can show the connection a little more detailed or a little less detailed as we want that. We can show some outlines and so on. A lot of things we can do with what we want to do before we want to print this into the printout report or just on a sheet of paper, or if we want to export the whole structure or the whole node into a DXF for further use in drawing, for example. Okay, that's so much for this pinned connection. We start a new case for a new connection. This is supposed to be a rigid connection, so we select rigid joints. In this case, we want to have a beam to column connection where we only have the option rigid end plate connection. So we select that. We have some additional settings for the force distribution in the joint, so we can determine the bolt forces, elastic or plastic. As we need to do that, we keep that on elastic, and we want to use the material of the main beam for other joint components. So we check the box and go on again to nodes and members. I select the node. I want to have the connections on the level number 1 on the outer frame nodes, just these 8 nodes. To select them manually one by one is a little, yeah, takes a little while, so I just go to my user-defined views where I have only the main frames and can just select these 8 nodes. So this is a rather quick thing. Okay, and default geometry as before. Mostly this is consisting of columns and beams that somehow connect to the node. In this case is 2 columns, 1 node. Most cases only at node number 13 we have an undefined construction status. So we have a look at that and we see that this is an additional beam in the other direction, so we can, that doesn't matter in this case, so we can just set it to inactive. And go on with the design. Go to loads, result combination number 1 again, and we go to the geometry. Here we a taper would be a good idea for this node. So we select a taper for the lower flange arrangement. So the taper is done below the beam that we are looking at. The profile of the taper is supposed to be a welded profile. So I go back to the cross-section library and I select a symmetric T-section with a height of 200 millimeters, a width of 300 millimeters, flange thickness of 15 millimeters, web thickness of 10 millimeters, and weld thickness of 5 millimeters. So I confirm that and I see that this taper is added. The length of the taper is supposed to be 400 millimeters, so it's getting a little smaller. And then we can have a look at the end plate. We want to have the end plate cut off below the flange of the beam, because if we have some grating or something, they would collide and that wouldn't look nice. So we can say the position of the end plate weld is supposed to be on the flange face. I change that and you see how the picture is changing. Also down here, it's now below the flange. The plate height is supposed to be the same as the height of our beam with a taper, so 500 millimeters, and the plate width shall be 300 millimeters. The plate thickness is supposed to be 25 millimeters. So this is pretty much what the connection is going to look like. The bolts are not in the right place yet, because this one collides with the flange of the taper, and that's not okay. And we want to have some more bolts anyway, so I changed that a little. I don't want to have a regular bolt distribution, so the height of the middle ones can change. Then I want to have a bolt diameter of M20 with a bolt strength grade of 10.9 again. And I want to have 3 horizontal bolt rows. So this changes, and I have to adjust the distances between the bolts. To P11, you always see the sizes, the names of the sizes in the picture on the top right, so you know what you're doing. So 160 millimeters for P11, P12 is supposed to be 200 millimeters, and now we see that looks a lot better than before. And then we change the web weld dimension to 3 millimeters. That's okay. I also have the option to use backing plates, which we are not going to do now, but they can be done on the back of the flange of the column. And we can also add some stiffeners, horizontal stiffeners in the column, and also diagonal stiffeners in the column to stiffen the web of the column. But that's all not needed here, and we can go on and calculate that. Here we have a maximum ratio of 84%, which is very good. Governing is the resistance of the weld of the end on the end plate. So there's still room for optimization, but that's okay for now. And we go on and make a new design case for a rigid splice plate connection. So again, we use the rigid joints. In this case, we want to have a beam-to-beam connection with this rigid splice plate connection. Same procedure as the other times. We select the node. Now the node is missing. I have to show everything again. I have to cancel the visibility mode, and I want to make this connection in a place where I have a little more moment. So node number 37 is the desired one, and I click on OK, set the geometry to default. A beam-to-beam connection is recognized by the program, and I go on with the loads, result combination number 1, and the geometry. Here we see a lot of bolts, and the connection looks quite good. For a rigid connection, we want to use a bolt strength grade of 10.9 on the web and on the flanges. It's not needed, but we use it anyway. And we want the bolt diameter to be a little smaller instead. Okay, this is it. I start the calculation, and we get a maximum ratio of 62%, which is okay, but maybe we could omit one of the bolt rows for a little smaller connection and a little less material that's supposed to be used. So we could also optimize that one, but since I still want to show you some more things, I go to the next case and make another rigid joint, but in this case a beam-to-beam connection with a rigid end plate connection. Again, nodes and members, and I select these two nodes next to this middle column. Click OK, default setting, yeah. Again, the beam-to-beam connection is recognized, and we want result combination number 1, and go on to the geometry. Here we want to do a few adjustments again. The end plate has to be, the weld of the end plate has to be on the flange face because of the grating I mentioned before, and that wouldn't look nice in this for this connection if there would be some grating like laying above the, on this connection. So we make this change. The plate height is okay at 330 millimeters, and the plate thickness we set to 15 millimeters. What else do we want to change? The weld thicknesses to 5 millimeters and 3 millimeters for the web weld. What else? The bolts. We want to have a regular, we don't want to have a regular bolt distribution, and we want to adjust it all ourselves. The bolt diameter is okay at M16 with a strength grade of 10.9 again. We want to have only 2 horizontal bolt rows and have to adjust the vertical bolt distances, 40 for the distance to the edge and 230 for the distances between the bolts. That's it for this connection. Looks quite good, and we do the calculation. Now we get a maximum ratio of 56%, which could be a little better. It could be optimized. So we go back to the geometry to do an optimization one time, and we can change the plate thickness. I should have shown you before that one of the governing is the T-stub in tension, and that means that the resistance of the end plate is one of the governing elements, and thus we can change the plate thickness and try it with 10 millimeters. Recalculate. And now we are at a maximum ratio of 77%, which is better. And yeah, you still have a lot of options to optimize this connection by changing different parameters. So now you've seen how all of these different connections are similar regarding the input. You can adjust any parameter to your needs and to reach the required utilization of the connection. And now I want to show you how the module, the results are shown in the main graphics window. I can show all the results or all the joints, all the cases in one picture. So here we have the end plate connection for the beam-to-beam connection, then the splice plate connection, beam-to-beam. Then we have the connections from the column to the beam, and somewhere here the fin plate connection for the pinned connection. I have another file which shows a few more joints. In this case, we all the joints of the main frames. So we also have some column bases with base plates and some anchors. Then we have the beam column to beam connections, also for the middle nodes, and one connection or two connections on the top level, which allow the upper beam to run over the middle column by just inverting the connection. So in this case, the beam and the column would be inverted in the module. I go to the module, oh, that's from the other file. I close that and go to the to this module in this file, and here we see the general data for this joint number 7. General data. And notes and members, okay. And here we see how this is done. So we have this node number 152. Here the beam is, or the column is defined as the beam, and the beam is defined as the column, and that way we get this inverted connection. Okay. That's about it for the presentation. I'll show you to the website. For those of you who have not used our programs yet, feel free to download a trial version of our programs of all our programs from our website, www.dlubal.com. Here you can download the trial versions. All our programs are available with full functionality for 90 days, which you can use to test the programs thoroughly. Thank you, Lucas, for your assistance and for answering the questions. If you didn't get an answer yet, we will follow up, sending you emails. Thank you for your attention and have a nice day. Bye-bye.